created by Mindsticks Foundation Trust.
Hello, learners, and a very warm welcome to this explainer. I want you to just take a quick moment and look around you. The clothes you're wearing, the food you eat, the medicines we take, and indeed the very cells in your own body, they all share a remarkable secret. They are entirely dependent on one specific element. So why is almost everything around us made of carbon? Today, we are going to unravel this fascinating mystery together, step by step.
Here is exactly what we will be covering today. First, we'll meet the carbon atom. Second, the magic of covalent bonds. Third, why carbon is everywhere. Fourth, saturated and unsaturated hydrocarbons. And finally, chains, branches, and rings. Let's get started. Section 1. Meet the carbon atom.
Okay, let's dive right into this. Carbon sits at atomic number 6 on the periodic table. What does that mean? Well, it means it has a total of 6 electrons. They are arranged with an electronic configuration of 2 electrons in its inner shell and 4 electrons in its outermost, or valence shell. Now, in chemistry, the driving force for any atom is to achieve stability, right? Which means attaining the electronic configuration of the nearest noble gas. For carbon, that nearby noble gas is neon, which has 8 electrons in its outer shell. Therefore, carbon desperately needs 4 more electrons in its valence shell to achieve this perfect stability.
Section 2. The magic of covalent bonds.
Now, carbon faces a really difficult dilemma here. Route 1. It could try losing its 4 valence electrons to attain the configuration of helium, but losing electrons leaves a net positive charge. To remove all 4 would require an immense amount of energy, creating a highly unstable C4+ cation. That route is impossible. Route 2. What about gaining 4 electrons? If it accepts 4 electrons to reach the neon configuration, it becomes a C4- anion. But carbon's nucleus only has 6 protons. Those 6 protons simply cannot hold on to 10 electrons. The increasing repulsive forces make it highly unstable. So giving or taking electrons, simply not an option for our carbon atom.
So what does it do? Well, carbon finds a beautiful and elegant solution. If it cannot give and it cannot take, it shares. This brings us to the covalent bond. A covalent bond is the chemical bond formed by the sharing of 2 valence electrons between 2 atoms, so that both attain a noble gas configuration. I want you to remember this concept clearly: sharing. Neither atom loses entirely, neither gains entirely. They cooperate to achieve stability.
Let us look at the simplest possible example to visualize this sharing. Here we have the electron dot structure of a hydrogen molecule. A single hydrogen atom has only 1 electron in its K shell and needs 1 more to become stable like helium. So, 2 hydrogen atoms come together. They overlap their valence shells and share their single electrons with each other. That single shared pair of electrons constitutes a single covalent bond, keeping both atoms perfectly stable and electrically neutral as an H2 molecule.
Now, atoms can actually share even more than a single pair. Just look at the oxygen molecule here. An oxygen atom has 6 valence electrons and needs 2 more for stability. When 2 oxygen atoms meet, they don't just share 1 pair, they share 2 pairs of electrons. This creates what we call a double bond. You can clearly see the shared electrons right there in the overlapping regions of the 2 circles.
And just to completely cement this mechanic in your mind, let us observe nitrogen. A nitrogen atom has 5 valence electrons and needs 3 more to attain stability. Therefore, 2 nitrogen atoms will share 3 pairs of electrons with each other, forming a triple bond. By understanding how hydrogen, oxygen, and nitrogen share electrons, we now thoroughly understand the basic mechanics of covalent bonding.
Section 3. Why carbon is everywhere.
10 million. I really want you to take a moment to process that massive number. There are about 10 million known carbon compounds. To put that into perspective, this number is vastly larger than the total number of compounds formed by all the other elements in the entire periodic table combined. From the cooking gas in your kitchen to the incredibly complex DNA molecules inside your cells, carbon builds it all. But how?
The answer lies in 2 fundamental characteristics of carbon. First is catenation power. This is carbon's unique ability to form strong, highly stable covalent bonds with other carbon atoms. It can link together atom after atom to create giant open chains or closed rings. Second is tetravalency. Because carbon has 4 valence electrons, it can bond with 4 other atoms simultaneously. It is literally like an atom with 4 hands, ready to grab onto anything, especially other carbon atoms, oxygen, nitrogen, or halogen.
And this brilliantly illustrates tetravalency in action.
Here we have models of a simple methane molecule, CH4. You can see the single carbon atom in the center, using its 4 valence electrons to form 4 single covalent bonds with 4 surrounding hydrogen atoms. It is the perfect simple foundation of carbon's building blocks, showing exactly how it satisfies its need for 8 electrons.
Section 4. Saturated and unsaturated hydrocarbons. We call these specific compounds hydrocarbons. It's exactly what it sounds like. They are the simplest and fundamental organic compounds containing only carbon and hydrogen atoms. Methane, which we just observed, is the very smallest hydrocarbon. Understanding hydrocarbons is the essential first step to mastering the vast, vast world of organic chemistry. Now, kindly observe the vital difference here. On the left, we have ethane, C2H6. Notice that the 2 carbon atoms are joined by a single bond. When all carbon valencies are perfectly satisfied by single bonds, we call it a saturated hydrocarbon or an alkane. But look on the right, we have ethene, C2H4. Here, the 2 carbon atoms must share a double bond to satisfy their tetravalency. Because of this multiple bond, we call it an unsaturated hydrocarbon, or an alkene. Generally, these unsaturated compounds are much more chemically reactive than their saturated counterparts. I want you to always let your eyes guide you to the bonds. Single versus double makes all the difference in chemistry.
Section 5. Chains, branches, and rings.
Look carefully at this molecular formula, C4H10. You have 4 carbon atoms and 10 hydrogen atoms, but notice how they can be arranged. On the left, they are joined in a continuous straight chain called butane. On the right, the exact same atoms are arranged in a branched chain, forming isobutane. Same exact number of atoms, completely different structures.
This remarkable property is called structural isomerism. It is the phenomenon where compounds have the exact same molecular formula, but completely different structural formula. Because the structure is different, their physical and chemical properties will be entirely different too. Structural isomerism further multiplies that staggering number of 10 million possible carbon compounds we discussed earlier. But carbon doesn't stop at straight or branched chains. It can even bite its own tail. Here is the ring structure of cyclohexane, C6H12. The 6 carbon atoms join together in a closed loop, or ring. This completely changes their properties yet again. Whether as a continuous straight chain, a branch, or a closed ring, the carbon skeleton determines the fundamental shape and behavior of the whole molecule. We have journeyed all the way from a single atom needing 4 electrons to the master builder of 10 million compounds and the very foundation of biology. So, I want to leave you with this provocative thought today. If carbon's unique sharing ability and tetravalency built all life on Earth, could another element with similar properties, perhaps sitting right below it on the periodic table, build life on another planet? Thank you for joining me in this explainer today. Keep asking questions and keep exploring the fascinating world of science.